Okay, so today, so I'll be honest, I'm not entirely sure what Professor covered yesterday. I was supposed to check that up, but I didn't. I kind of got busy, but I do know that there was a request put in to do support vectors. So I want to talk about that. I want to talk about kerneling functions because I feel like those are just super, super cool. Not the most intuitive concepts, but once you get them, it's like, what? This is too cool. So we're going to cover that. Then we're going to talk about normalization, sort of how, like what that is, how it is. We do that in both the project and the homework. It's basically like all of question 2 is about normalization. So I do want to talk about that. And then I want to talk about cross-validation as well. And we do have some sample code too. So hop on over to the website. We're getting back in touch with our little avocados. So yeah, it's going to be a good time. So support vectors. So these are probably conceptually one of the more easy machine learning classifiers to kind of conceptualize. But essentially a support vector it sort of carves your data. So if you think about like so let's take a binary classifier. So you have data that's divided into 2 classes, clustered in a certain sort of array. It essentially takes a hyperplane, and I'm going to tell you what that is in a moment, and it just kind of just cuts it in 2. And so like if you look at this first graphic here, 2-dimensional space, a hyperplane, it's just simply a line that carves your data in 2. For a 3-dimensional space, it's a plane. And it's a little bit difficult to kind of conceptualize when you get above 3 dimensions, but conceptually, it's kind of the exact same thing. That as your data kind of gets cast out into n-dimensional space, and dimensions in this case are associated with your features. So each feature is sort of an associated vector and associated dimension. And so sort of a hyperplane, again, is just that sort of, I don't want to say line or plane, but it's essentially that kind of thing that just cuts a nice, neat linear line. And what's cool about it is it can be represented very trivially. It can be represented as just a kind of a simple quadratic equation with, again, each feature, each dimension sort of having its associated coefficient that sort of details the associated vector into that dimensionality space. So that's essentially on a very high level what an SVM does. It just kind of creates that hyperplane, and then it says, okay, well, anything on one side of it is this class. Anything that falls on the other side is another class. Very, very simple. Here's kind of where it starts getting a little tricky, though. So I understand that I can kind of I can sort of draw a line through my data set. The question is how exactly I draw my line. Because, and as this sort of example here sort of nicely illustrates, there is theoretically an infinite number of permutations of lines that will cleanly cut my data into 2. But how do I know which one to choose? So that's kind of the trick that an SVM has to try to figure out. And the way it does it is it uses these support vectors. So what is a support vector? Support vectors in this case are your data will sort of subselect the data that kind of lies closest to the dividing threshold. So in other words, these are the data points that are the hardest to define. They're the hardest to classify because they're sort of right up against the edge there. And these sort of the subset of your data, this is what known as the support vectors. And so what we then do is we take these support vectors and we try to kind of fit a line that then maximizes the total margin between those things. Because if we think about this again, if our goal here is to create a model that will generalize, chances are it will generalize if we have the greatest associated margin with it. Because then if anything kind of falls closer to the dividing line, that will be the thing associated with it. Oh, excited. Okay, guys, my lunch is here. Yay. So you guys aren't the only ones eating now, and me staring jealously at you while you're eating. So that, in short, is kind of what a at a high level what it does, it takes the subset of your total. So if you think about like a KNN as a model where the entire data set is fed in and is sort of used to train your model, an SVM takes a small subset, again, those support vectors, kind of the key decision points that will influence so again, it's actually the opposite way. The line is defined by the support vectors, not the other way around. The support vectors are simply the set of points that fall nearest to your opposite cluster. So if you're looking at kind of like relative distances, you're looking at the line, the series of lines that sort of fall closest to it. And those are the ones that sort of define the relative distance. So like, for instance, sort of hypothetically, if you were asked on the homework about a support vector, and then you're asked about like whether or not a particular point will influence it. Well, just visualizing it, if the point is within this, then yes, it'll be a support vector. It's something that is going to impact it. If the point lies up here, then it really doesn't matter at all, because your model, you're only training your model on these few series of points here that are right up against the edge, right up against the margin. And then again, then it just becomes the notion of trying to find a line that maximizes the margins between those support vectors. So simple, easy, makes a lot of sense. We're done here, right? On to the next topic. You got it. SVMs, we're good. All is good, right? So not quite, right? So these examples here, we sort of had these nice, beautiful, clean delineations between our data set. Real world never quite works that way. Data sets are almost never fully linearly separable. So it can be very difficult to sort of create that hyperplane. And how, so then in that instance, in the instance where, let's say, you know, going back here, let's say we have a blue line that creeps over here. We have a red line that creeps over here. How do we handle that? So at a high level, I mean, there are a few things that we can try to do. At a high level, though, there's sort of two things. So the first thing we can do is soft margins. So that says we kind of anticipate that, you know, there's going to be some noise in our data set. There's going to be some points that really aren't statistically representative. And like, we're okay, like we're still going to do the hyperplane, and we're going to just like accept the fact that there's going to be some things that aren't going to fit perfectly with it. So that's a soft margin approach to this. The other approach is kernel functions. All right, our kernel functions. Finger licking good. So kernel functions is the idea that we can kind of extend our feature space. We can kind of, and again, I'm going to give you a specific example. I'm just going to throw up the topic. You're probably not going to get, and that's okay. I'm going to like give you an example that hopefully will make it very intuitive for you. But we sort of extend our data frame into sort of an extra dimensional space that will then allow us to achieve that hyperplaning separation. So in this example, so if our data sort of originally was here and we don't have kind of a nice clean linear delineation, we cast it into this higher dimensional space. And then there's that nice, beautiful hyperplane that we can then sort of use to carve our data and do that. So if you are like me and you first learn about kernel functions, your approach will probably be something like I did. And I was like, what in tarnation would cause pure dimensionality expansion to suddenly make my data linearly separable, right? Unless I am inventing new stuff about my data, unless I am making up information that doesn't exist, how is it that I can somehow magically go from something that is not linearly separable to something that is? That just doesn't seem particularly okay to do. So let's work through a sort of a specific example here. So let's imagine that we have a single feature data set. So we have an X, you know, in this case, it's an X1 feature data set, and it has an associated labels. So let's say our blue squares are 0, our orange circles are 1. So in our current sort of one-dimensional space, this data is obviously not linearly separable. Now, the key thing to note here is that there clearly is a delineation between them, right? We can very obviously, just eyeballing this, we can see that, oh, if we could do like a non-linear, like maybe like a circle or something, we could make a nice clean separation. The problem is it's not linear, and SVMs operate on a linear thing. So there is the potential for clustering, it's just not there. So what do? We take it from a one-dimensional space to a two-dimensional space, and we apply sort of a uniform transformation function to it. So in this case, we're going to take our one-dimensional space here. We're going to keep that initial dimensionality x, but we're going to add a second dimension, in this case, x squared. So we take all of our x values, we simply square them, and now our data is cast onto a two-dimensional plane. And when that happens, suddenly that data here becomes linearly separable. And here's an example here where we're casting a two-dimensional space that isn't linearly separable onto a three-dimensional space, and then suddenly we can sort of take a hyperplane and it works. Now, I think sort of a key thing to note with this, and hopefully that kind of helps make it a little more intuitive, but the important thing here is that you're not creating new information. You're not sort of inventing new stuff about your data that wasn't there. You are simply representing it in a new manner. That pattern, in order to classify, was already there. That pattern was already latently in your data. You just weren't expressing it properly. And so by casting it into that higher order, higher dimensionality, you're able to sort of represent that. And another thing to say that it's not just about transforming it. A key sort of additional thing about this is there is value to taking it into a higher order space. And that's simply because by increasing the sheer volume in which you are trying to sort of achieve that hyperplane, almost statistically, you will almost always kind of get to the point where you can achieve a hyperplaning type solution. And that's because, again, if you look at your area here, so let's imagine this is a 3x3 square. Your surface area there is 9. By adding that new feature, your surface area goes to 27. And suddenly, right here, we have 3, 6, 9. So we have 10 points. So right here, if you think about our feature density, you have 10 bullet points cast over a surface area of 9. Here, you have those same 10 points, but now cast over a sort of a volume density of almost 1/3. So we go for a little over 1 per unit measure of density to now 1/3 per unit density. So statistically, as your feature space becomes sparser and sparser relative to the total volume, it becomes almost a certainty that you can kind of achieve that separation. And I do kind of want to mention that because remember, we were always kind of talking early on about like one-hot encoding and why one-hot encoding, it can be a problem if it becomes too highly dimensional. And this is precisely why. Because if you throw in enough dimensions into your data set, it is almost certain that you can achieve a sort of a clean parsing of your data, at least within your training model. It's almost a certainty that you can do that. Now, the problem is, and this kind of gets into that thing of overfitting or not. So, you can achieve something that looks like that if it goes into high enough dimensions. The problem is that model something that has any utility, any generalization in the real world, or have you just simply overfit the heck out of your model? And really what that comes down to is the amount of sort of useful information, the amount of entropy that are contained in those features. Like you can add features to that. So, a kernel, by definition, we're not adding new data to our data set. We're just simply reframing it. So the amount of entropy in our data set hasn't changed. We have just taken that same entropy and taken it into a larger dimensional space. PCA can sort of do the same thing. And if it goes too much, you're then overfitting, but you're not actually adding relevant information. So that's what we're doing with a kernel function. It is good. It can be a very useful tool because, again, without it, oftentimes we won't necessarily achieve kind of a clean parsing of it. But again, it's like, and this is something like when we talk about normalization, we're going to go kind of back and forth on this. it's the kind of thing where it can be a good and important tool to achieve that classification. But if you take this too much to any extreme, you begin to overfit your data. You overlearn for the particulars of your data, and you start incorporating, and we're going to cover all this in a little bit, but you start incorporating noise into your data set instead of learning the underlying sort of patterns of your data. So then, Drew, to your question, so again, there's a trade-off of casting it to a higher order. Theoretically, right, in this is a good example of, I did take it to a higher dimension, but by doing so, it allowed me to tease out an underlying pattern that I wasn't able to get otherwise. So in this case, it's actually a really good thing. In some cases, maybe like this, it's maybe not as good a thing, because what I've ended up doing is sort of overfit to that model and create something that really isn't representative of the broader universe of data. So, and then just kind of one thing I'll say about this is that there are different types of transformations. So I gave you this one simple example where we do, where we just kind of take our input feature and then we just square it. And that's the thing. And there are sort of a number of different kerneling functions that you can use. The default one for this is what's known as RBF. And RBF is really good. It's a nonlinear function, and it's really good for sort of achieving a linear hyperplaning of nonlinear data sets. So if your underlying data is inherently nonlinear, something like an RBF tends to be really good at potentially achieving that linear separation. Other ones are kind of better tuned for the specifics of your data. And this kind of goes back to just a general question. Do you know which kernel function will be good? You don't necessarily know. You may have some intuition about your data and how it's structured, but until you try different kerneling functions, different approaches, you won't necessarily know. And that's part of what we have you do in Project 2 is we say, yeah, run an SVM, but try these different kerneling techniques and see if you can kind of achieve better performance by kind of casting it into a different n dimensionality space. So I think that's what I wanted to cover in terms of from a theoretical model in terms of SVMs and kerneling. Let me go now to the data set. So we're going to go back to our avocados. If you haven't downloaded it yet, sample code is here. But let me just kind of pause while people are pulling that up. Any questions on what we just covered materially? Okay, you guys are feeling that? Cool. Okay, so episode 2, Revenge of the Avocado Squad. So remember so when we first kind of saw our avocados, we did, at the time we had done two things. We ran a linear regression to try and predict the price of the avocados. And then we did a classification exercise to try and predict whether or not a given avocado was conventional or organic. So we're going to stick with that second one. And so all of our initial code here is pretty much what we had already worked with. So, we have our little avocados. We can look at our data set here. We're just checking if any of them is null. These are all things that you have seen before. We're pulling out our labels. We're pipelining it. And actually, let me just pause there because there were some questions about pipelining in homeworks and stuff. Are you guys feeling okay about pipelining, particularly in the context of Project 2? Okay, you are an agreeable bunch. I love it. Okay, sure, we can go over it again. Absolutely. So so this is, I'll just use this sample code as an example of it. So again, the whole notion of our pipeline says, once we've kind of established how we want to process our data, what transformations we want to do, we just kind of want to make a nice, simple, single function call that we can just plug in any new data that comes in, and it'll output the process data we then want to fit into our model. And generally speaking, there are sort of a set of really consistent types of things that you're going to want to do to your data. So we talked a lot about scaling your data and how important that is, particularly for your numeric features, how important it is to scale them. And in project 2, we have you do that. Actually, we kind of say, hey, plug your raw data into a KNN and then plug a scaled data set into your KNN and just look at, having changed nothing else, hopefully look at how dramatically your performance improves. It's the same data. You have just, again, that whole sort of recasting it in a way that makes it interpretable to your model. But so you guys are good on the whole scaling thing, right? Conceptually. If you're not, let me know. We can continue talking about that. But scaling is something you want to do. Generally speaking, you want to do an imputation strategy. Now, even though here I don't do an imputation strategy because I looked at here, I'm like, oh, there's no nulls. Great, I don't have to impute. But that's not actually generally something you should do, just because if this model goes into production, you have to anticipate that in the future, you are going to get inputs with null values. And so as a, once this model is live in production, consumer facing things, people will be filling out forms, people will just inevitably leave information blank. And just because your training data happens to be nice and clean and perfect and beautiful, doesn't mean it will always be the case. So in general, I didn't do it here, but in general, it's always a good idea to have some kind of imputation strategy, some kind of mechanism to catch null values in production when they happen. I think we've kind of gone over that in detail, but again, just stop me if you want to talk about any of those things, but that's usually something good to kind of include in your pipeline. And, last but not least, kind of just figuring out what you want to do with your categorical variables. So, the most obvious thing is you may need to transform them. So the first thing is, if your categories are not in a numeric form, you're going to have to transform them. So you're going to have to, if you want to include them in your model, they have to be transformed. You either have to do something like an ordinal encoding, where you assign sort of an associated kind of structured numbering to them. You may want to do a one-hot encoding. Again, all things that we've discussed. But you sort of want to, and that's basically kind of the things you want to do. And then last but not least, augmenting your features. If you want to sort of create and manufacture new features, and I think we talk a little bit, particularly in the homework, about kind of thinking a bit more creatively about like feature crosses and sort of useful features that you can kind of use to sort of intuit patterns in your data that aren't necessarily tractable from a purely linear perspective, but do exist. And again, it's all about the notion of like, you're not inventing new information, you're just taking information that is latently in your data set and just recasting it in a way that makes it something that your model can then digest. And that's really kind of an important thing to understand about the augmentation and in general with all of these things. So yeah, but so in general, and so there's a question about imputation, right? Yes. So particularly if you're moving into a production environment, you do kind of, you may, so the only exceptions would be if it's like a required field. So imagine that you have users inputting a form. If the thing that they're inputting is a required field, then maybe you don't need an imputation strategy in that case, because then there will never be a use case where they'll be feeding in null values for that. But in general, yes, unless you want your model to break in production, it's always a good idea to have defined imputation strategies for it. And the cool thing about it is you can always do different strategies for different features. You don't have to, like, the nice thing about like creating these different pipelines is, right now we broke it down in terms of categorical and numeric, but you can also break down within numeric. You can treat different numeric features differently. You can sort of create these parallel pipelines. You can treat different categorical ones differently. You're not limited categorically by the types of data you have. You can treat half your categoricals one way and create a specific subpipeline for that. And you can treat some of your other categoricals in a completely different way and make sort of just custom rules for any particular feature. But yeah, as a general rule, it's always a good idea, again, when you're moving into production environment, to have an imputation strategy. But yeah, good question for that. So So did that answer the specific question about pipelining, or do you want to, I don't know if you want to get into more of like the weeds of the actual code itself and the actual implementation, or if you were asking more at sort of like a high level, like why are we doing this type approach? Okay, no, okay, cool. All right, good. Awesome. So we have our,
I don't have a quick question, actually.
Maybe.
So these are all kind of using existing methods like standard scalar and one-hot encoder and stuff like that. If you wanted to do something a bit more custom, would you just define a function and feed it into the pipeline?
That's exactly right. And you can sort of see right, in project one, that's precisely what we did with our augmenting features.
Okay.
In that case, we didn't have sort of a nice pre-built Python library that we could just cleanly fit in. So we did have to kind of manually hard code a function. But yeah, there's nothing stopping you from devising your own function and then just passing it in as a strategy.
Okay, cool. And I'm assuming that there's like a template for that, right? You have to account for certain parameters and stuff.
Yeah, I mean, there'd be, there obviously are, you'd have to test that and debug it and, work with your data and ensure it works. But yeah.
Okay. All right, cool. Thanks.
Yeah, absolutely. And cool that you're thinking along those lines.
I had another question about the pipelining.
Yeah.
I see that we drop the region feature, but then how come you still keep it in the categorical features if you dropped it?
Oh, that's a good question. Oh, okay. Yeah. So in this specific case, what essentially I'm doing is I'm defining my, okay, so let me kind of just quickly, 2 minutes, just walk through the what I'm doing with each of these steps. So this is obviously our high level call. So this is the new array of pipeline data that I'm creating. And I'm running that by calling full pipeline, which is essentially my recipe that I'm going to define for how to pipeline the data. I'm calling the fit transform function, which is again a previously defined one. I'm calling it on my, in this case, I'm calling it new x just because I'd used that previously x for my regressions, and now I'm doing that. And then I'm just casting it to array to make sure it properly gets transformed into a NumPy array. Sometimes you don't have to do that. Sometimes you do. I'm actually not sure why, but like if you're getting errors in terms of that, that's always like a nice, easy thing that you can do to fix that. Full pipeline. So full pipeline again is like our recipe. And here you're again calling the column transformer function, which you're importing. And then you're sort of creating your set of rules. So the first thing I'm saying in this case, I'm going to have two sets of rules. I'm going to have my numeric rules and my categorical rules. And my numeric rules, I'm going to run them on my numeric pipeline. Or sorry, I'm going to run the numeric pipeline, which is again a set of instructions I'm going to define. I'm going to do it on my numeric features. And then I'm going to, in this case, I don't need to sort of define a formal pipeline for it because I'm going to one-hot encode my categoricals and then do it on my categorical features. So then I need to sort of define these things for a numeric pipeline. Again, I define it here. It's just my little pipelining. And then in this case, I'm just scaling it. But again, you'd probably want to do an imputation. You may want to do some additional things in terms of augmentation or something that would all kind of fit in there. The thing, and this gets specifically to your question, I then also need to define what features I run it on. So my categoricals, in this case, my categoricals is just region. So I'm going to take region and I'm going to one-hot encode region. My numerical features are going to be essentially everything that I'm keeping in my pipeline except for region. And so that's why here I'm first sort of taking my original data frame, I'm dropping region, and I'm defining that as my new avocado numericals. And then just my numerical features is just the list of categories associated with that. So to your question, the reason I'm dropping it but then including it is it's not that I'm dropping it from my overall data set, I'm dropping it from my numeric data set. So I'm pipelining these using my numeric pipeline, and I'm pipelining this using my categorical pipeline.
Okay, that makes sense. And then I guess specifically for the project, if we dropped a column before doing this pipelining part, then we wouldn't even have a categorical feature category if that was like the only categorical feature, right?
Correct. Exactly. The pipeline, there's no sort of firm, and in fact, for project 2, let me just say generally, we don't give you like a lot of freedom in terms of what you do. Pretty much the only space where we're like, hey, play around with this is in terms of your pipeline. And the only thing that we specifically say is for your numeric features, apply a standard scalar. That's the only thing that we tell you to do, but everything else we leave up to you. So if you just decide, screw this, I don't want to deal with categoricals, I'm going to drop every categorical from my data frame, that's fine. And then in which case there's no need for a whole categorical approach. You can just do numeric. But yeah, there's no, it's all based on what you want to do with your data and what data you want to do it on. Okay, we're on my FM before pipeline. Okay, so there's a good question about like, can we augment before pipelining? So you theoretically, so let me just say this. There's no kind of hard and fast rule that says you have to do all this in a single pipelining step. And I'm sorry if I kind of give you guys the impression that it has to be that way. So what we're really, you could do these in discrete stages. But the whole idea here is again, moving from a development environment where you're kind of working in Jupyter notebooks and you have your discrete steps and everything is nice and neat, to, again, a production environment which this is uploaded into a server, this is running remotely, these are sort of automated Python scripts that you're doing. You could totally, as data comes in, you could first do kind of a discrete augmenting step, and then a discrete imputation step, and then a discrete thing, right? You can do all of those as discrete steps and just kind of like call them in sequence. There's nothing that stops you from doing that. This just happens to be like a really nice, elegant way of condensing that that assembly line into kind of a nice single function call. But yeah, there's nothing that would prevent you from doing it in sequence. Okay, so let's see. There's another question. How does column transformer differ from? So good question. And I have to be honest. So Shuniketh is asking about like the difference between column transformer and pipeline. And I will be honest with you, I haven't read the documentation on these that much, so I don't actually can't specify these. My understanding is that the column transformer is actually kind of applying the transformer, whereas the pipeline is just simply defining the approach. I don't believe pipelining actually does a transformation. I think it just sort of structures, it sort of takes your inputs and structures it in terms of how to approach these things. But again, I may be wrong, but like the code that I'm working off says you actually, the column transformer is what does the transformation, and the pipeline just defines the instructions that then go into it. But I haven't read the documentation, so I can't tell you that for sure. But I can't, let me put it this way. I know for sure that this way works. I'm not for sure. What's the purpose of the, okay. Oh, okay. Let me see. Oh, so you're asking me, what is the, oh, you know what? I'm sorry. There is no purpose to that line. I'm sorry. We can copy that. That, I think that's something I copied over. That's, I think, useful if we are, what am I doing for transform? Why did I do that? This is one of those things where you have these legacy codes and you're copying and pasting it and you forget why it was there in the first place. But I don't know why I'm doing a fit transform there, and I'm not even using it for anything. I think you use it for as part of your augmenting thing, I think. But, and if somebody just kind of happens to know that, but yeah, it's not needed for this thing. So I'm glad you flagged that. But yeah, that's legacy code. I copied it over to make this example, and I didn't really kind of think through what that line is doing. But yeah, you should be able to just run this. Let me just run this and make sure it doesn't bug out on me. Yeah. So again, for our purposes, it's not required. Again, I think it's an augmenting thing. Okay. Any other pipelining questions? Okay. Final step of the pipeline. Oh, okay. Okay, so Rob's got some thinking here. I think the final step pipeline. Okay, so Rob is talking to Srinikath's explanation, but yeah. So I'm not gonna do it because I'm just gonna admit I'm not fully versed on the specifics of what the libraries do, and so for me at best it would be speculation, but yeah, definitely look into it more. And if you guys are interested, I can do the research on that. I don't want to tell you that I can't or won't. I just at the moment I'm not prepared to talk informatively about that specific thing. Then going through this, we run our label encoder on our labels. We just kind of generate our, we output our feature space just to kind of make sure that we do a train test split. We output our feature space. Again, we kind of do our sanity check just to make sure same number of columns across test and train, same number of labels. Now it looks good. We ran our logistic regression. We output our accuracy thing, and we're good to go. Okay, now here's the new stuff. So, so in terms of how you would actually do a SVC, it looks pretty much, and this is true of, the nice thing about like scikit-learn is that the same framework is pretty much true for no matter what model you do. Like even though these are vastly different models in terms of what they actually do with your data, from a user perspective, from in terms of how you load the model, import it, do it, you pretty much are going to do the exact same set of stuff. So in this case, what you're doing, and just to kind of walk through each of these steps, in this case, you're defining your specific instance of your model. In this case, SVM will be my specific instance of a support vector classifier. Now, quick and dirty, interesting thing here about probability equals true. So some models will innately give you a probability associated with a classification. Can anybody, just off the top of your head, think about a model that we have covered in lecture or whatnot that sort of returns an associated probability of a classification? Yep, logistic regression, excellent. So innately, there isn't a probability associated with it. And so if you guys recall, when we talked about ROC curves, remember, so we said, first you apply sort of a learning model to your data. You try to learn something about the data. In this case, you learn an associated probability with a classification. And then there's that added step. And that added step is a decision function that says, okay, well, there's never going to be 100% certainty or 0%, or almost never 100%, 0%. It's always going to occur on a threshold. And I need to choose somewhere to carve that line. Like if you think about the logistic regression, that sigmoid function, you're sort of casting your different probabilities and you're sort of creating a clean sort of linear divider where you're like, okay, everything above this point, everything above this probability is, I'll give it a label of 1. Everything else will just be label 0. So there's that associated probability. And if you recall, when we looked at like ROC curves, it was looking at how cleanly your data would sort of assign true positives versus true negative or false positives, depending on sort of how strict your decision threshold was, right? It was that 2-dimensional curve, but we said really there's that 3rd dimension, which is the associated probability. That's as you start with like 100% certainty and you go down to like 90, 80, 70, 60. And at some point, right, you're going to be admitting more and more true positives. But at some point, you're going to start like your false positives will start to creep in there. Because, like if something has a 70% probability of being 1, well, 70% of the time you're going to get right, but 30% you're going to get wrong. And so you are going to get sort of more and more false positives in your data, the lower your decision threshold goes. And that was what that ROC curve was looking at. So all that is by way of saying a lot of models have that probability baked into it. SVCs don't, because if you remember our whole thing about SVCs, where is my thing? SVCs are just a hyperplane. SVCs are, this is the thing I wanted. SVCs, I'm literally just carving it into 2. I'm not associating a probability with it. Now you can theoretically try to maybe do like a proximity thing. There might be some nifty thing you can do about like probabilities associated with it, but SVCs just in general are not probabilistic models. Here's my line. Everything above it is green. Everything below it is red. And I'm not associating relative probability of this line versus this one. But if we want to do something in ROC, we do actually need to have that probability. We need that decision threshold. And so one of the really cool things that this does is it says, well, by default, we don't run it, but we actually can generate probabilities. And the way we generate probabilities is we run a cross-validation when I'm training this model. And what that means is basically instead of running one SVC, I'm running multiple SVCs again, and we're going to get into the whole cross-validation thing. And I'm seeing, each time, basically I'm kind of sampling what's the label for this time, what's the label for this time, this time, this time, and then giving me an associated probability of that label. So if I run 10 SVC models, what's the probability that it's going to sort of land up as 1 each time? So I note that because the default is not to run that, because that's only useful if you're doing an ROC curve. If you're not, you don't need your probability score. You can just get your metrics without it. And as you can imagine, doing a cross-validation dramatically increases your computational time. Like you'll notice, like when you run the model, like if you run a logistic regression and you clock it, you should get that accuracy like really fast. You run this cell, this will take you considerably longer. But if you just go to the default probability equals false, it'll just run the single model and it'll return very quickly. So all of that is just by way of explanation of what that whole probability equals true thing is doing. So then remember, we've defined this as like a particular instance of our model. So to get that, we then have to run that fit function. And I'm doing it on my training features and my training labels. So now I'm training my model off that. I'm doing the fit function. And then this is now, SVM is now my fully trained SVM model. So then I can then apply that newly trained model to get my set of predictions. And so to do that, I just kind of use that model. I run the predict function to say, let me plug in my test features to get a set of predicted labels for it, which again, when it comes to all of our metrics, is going to be critically important. And then the last thing is our score. Rather than doing a predict, I do the predict probability. And again, I associate the probability associated with my test features. And again, that's important when we're doing the ROC curves. So that's sort of each line, and pretty much every learning model that you're going to do for project 2 and even beyond, you'll generally try to follow that just general framework. They're kind of all structured in that manner. So then metrics, so scikit-learn has a really great kind of thing. You just import metrics, and then you can just call your metrics functions. Thank you. As so again, we have like our accuracy score, and you guys remember we kind of covered differences between accuracy, precision, recall, F1 score, right? We covered all of that last week. So hopefully you guys kind of have a good feeling about that. But I will pause to see if you have any questions around that. And then confusion matrix. And by the way, so we have, there are default confusion matrices as part of scikit-learn, but just they're not really visually very intuitive. And so that's why we have this little helper function here, the draw confusion matrix. And for that, it's very simple. For that, you're simply, there's 3 inputs. You put in your actual labels, your predicted labels, and then you just put in your sort of, I guess, column values associated with. So plain text column values for that. And that's what you use to then generate this. So, all right, so let me pause there. And let me just see if you guys have any questions about implementing SVMs, metrics, so on and so forth. Okay, I don't understand where. Okay, yeah, so again, so probability equals true. So, sorry, hang on a second. So the whole idea is kind of going back to ROC curves was, in general, many learning models there's kind of the two stages to how a classifier works. And the first thing is it learns a model of your data. And then based on that model of your data, it applies a decision function. It decides, it has to kind of make, if you're doing a binary classification, it has to decide, okay, if sort of an if-then condition. If this is satisfied, then assign label 1, otherwise assign label 0. So that's your discrete sort of decision function that you then layer on top of what you've learned about it. And there's different kind of ways in which your model learns it. And so something like a logarithmic classifier or something like a naive Bayesian classifier rely very heavily on probabilistic models. So they generate a probability associated with a classification. So when you're looking at your distribution of data, there's going to be an associated probability. There's the probability of this being read is obviously much higher than this probability, and so on and so forth. So there's associated probabilities, and so for something like Bayesian or logarithmic, they just naturally have those probabilities. And so then a decision function for there says you have to define kind of what your probability threshold is for when you just assign a label or don't. And if you want to be very strict, like if you're very worried about, for instance, false positives, you may set your threshold very high. You may say, I'm only going to assign this label if I'm 90% confident. If you're very concerned about false negatives, you may do the opposite. You may say, as long as there's a reasonable probability, as long as there's like a 30% probability that this could be the label, I'm just going to assign it. Who cares if I get a bunch of false positives? I just want to make sure I'm not missing anything. And so that's where kind of your decision threshold comes in. And that's where things like precision and recall become so important in terms of like how you structure your thing. And again, an SVM doesn't work in terms of probabilities. An SVM is a very kind of simple linear decision boundary. It uses your support vectors to define that decision boundary. And then it's just a very simple, the decision model there is anything above this line is 1, anything below it is this. Anything above the hyperplane, below the hyperplane. There's no associated probabilities. And so, so if we want to do something like an ROC curve, where again, we look at like the sensitivity to it, we can't do that natively with an SVM. Because again, we don't have those probabilities kind of baked in. And so all we're doing when we say probability equals true is we're saying, actually we do want to generate those probabilities. And the way we do that is we sort of create our own sort of artificial sampling by doing a cross-validation. In that case, we would run the SVC model multiple times. We would see how that particular sort of label gets assigned each time. And then based on that, we would associate a probability with it. So if we run our model 10 times and 7 out of 10 times it gets assigned to a particular label, then it would have that probability of 0.7. And then I would use that probability if I was then generating an ROC curve for it. So, but again, precisely because SVCs don't natively do that, and it's much more computationally it's much more computationally difficult to run. You don't do that natively. So that's only if you specifically are interested in generating an ROC curve. Okay, cool. All right, so we feeling that? Any other questions? Okay, then let's pivot back to the slides. Okay, covered all that. All right. Yep. Oh, hey, I got this meme. I feel like this is probably something week 1 you guys weren't going to get, but now this should be like old hand for y'all. Okay, so now we get into normalization. By the way, I'm keeping track. This is the second Star Wars meme. Pop quiz. This is the second Star Wars meme I've included in the notes. Does anyone remember the first Star Wars meme I included in the lecture? I feel like I'm going to talk to the professor about making the memes part of the exam. It's just important. Baby Yoda. Did I do a Baby Yoda one? I don't feel like I did a Baby Yoda. Did I do it? I don't think I did Baby Yoda. It's a good guess though. Baby Yoda is just prime meme material. Oh man, did I forget my own memes? This is bad. Oh, you're right. I did a Baby Yoda. Yes. Okay. Oh, you're right. Okay, hang on. Yeah, we did a Baby Yoda. We did it for train test split. We did a whole like Mando and Baby Yoda were having that moment, like, you know, can't leave you. Yeah. So when we were talking about train test split, we did a Baby Yoda one. Okay. We also did a Mando one. We were talking like, this is like week 1. We were talking about like using Anaconda, and I did a whole "this is the way." Yeah, exactly. Okay, awesome. Oh crap! There was a Luke Obi-Wan one. Okay, turns out I did a lot of Star Wars ones. Never mind. Okay, well apparently I failed my own exam here. But oh, just can't. I actually just wanted to test you guys. Ha ha ha. Anyway, let's talk about concepts of variance and bias in your models. And I do believe that the professor has talked about these in lecture. So are you guys kind of familiar with the concepts of variance and bias and how they apply to this? We have this nice little write-up on the slide here, but is that something you guys intuitively have a grasp of, or is that something we should sort of talk through? Okay, well, I'm not hearing either way, but because I made the slide, so I'm going to go through it anyway. Just kind of, I guess, taking a step back conceptually. When we sort of doing data science and really, you know, underlying data science, there's always the thing, you pull back the mask of data science and hey, actually you're running statistics. It's always this idea that like we're taking sort of a small sample of the broader universe. And you have this data set, and we want to use that kind of small subset of the total universe of data to try and infer a pattern about the broader world. And that, I mean, generally, again, that's what you're doing in statistics. That's really what you're doing with data science as well. You're taking your model and you're trying to kind of infer a broader pattern that's going to be applicable to the universe of data that you want to work with. Inevitably, though, there's going to be kind of problems with that approach, and that's kind of inherently the challenges you get in again both statistics and data science when you're looking at your data. Like, how do you kind of make sure that the approaches that you're taking sort of best match the overlying thing? And there's really kind of 2 ways in which those problems can sort of arise, and they kind of go in opposite directions. The first is variance. So it's the idea that the reality is, like, in the real world, nature rarely kind of follows this nice, beautiful, clean causal pattern. And actually, if it did, those problems by definition, you probably wouldn't be using machine learning on, right? If there was a nice, clean, linear relation, correlation, causality between certain variables, you wouldn't need to run convolutional neural nets or things. So in reality, those sort of nice, clean patterns don't really exist. And as a result, you don't always know kind of whether or not a particular data point is representative of a broader trend in your data, and it's something that's important to capture, or if it's what we consider noise. So there's always this concept of entropy, and it's the amount of sort of useful real data, useful real information that's captured in your data versus noise that, again, is it's outliers. It's not relevant to constructing the model. It's there, but it's not a statistically relevant thing. It just happens to be because you downsampled your thing, you happen to end up with that thing, but it's not really reflective of the broader universe of things. So the problem is, if you overlearn your model, if you try to kind of fit a model excessively to that data, inevitably you're going to capture the noise. You're going to take that noise, that thing that really doesn't reflect broader patterns in your data, and you're going to incorporate it into your model. And that's really what sort of a variance is. So And so, you know, and again, this is kind of an overexample. And that's sort of the classic example of overfitting, where you try to sort of parse it down precisely to there, and you know, to the point where, again, you've had a model that is just so specific to that particular snapshot of your data that it really has very little applicability generally. So bias is almost the bias is not almost, it literally is the opposite. Bias is the idea that you're looking at your data and you're saying, I'm going to make some simplifying assumptions about my data. And the most obvious example of those simplifying assumptions is most of these learning models are precisely that. Something like an SVM is an example of a simplifying assumption. Here, I am saying, you know what? There is a nice, clean, linear hyperplane that will nicely carve the data, right? A linear regression. There is a nice, clean, linear trend line that will nicely sort of predict my data. So I am making sort of this assumption that there is this sort of clean simplification to my data that can fit a model. Now, if I'm overly biased with my data, if I simplify it too much, that results in the exact opposite problem, underfitting. This is something you see here. Like we can see just eyeballing this, clearly there's some kind of, you know, convex sort of sloping line here we may want to capture, but instead we have biased our approach so much that we just have a linear thing there that, yeah, it's not the worst predictor, but clearly it's could be a lot better. And we kind of, obviously our goal in machine learning data science is to kind of achieve this low bias, low variance thing where we are capturing the broader trend in our data, but at the same time, we aren't like over learning the specific variance to the point where we're capturing that noise and not the underlying signal, the underlying pattern. So, okay, quick note. So how do we correct for bias? We're going to, at first I was going to actually cover this today. And then I was like, this is too much. I want to devote like a whole discussion section specifically to this. But at a very intuitive level, we minimize our bias by training our model. That's the whole kind of idea of trying to fit a model to our data, right? We start with a very high biasing, but as we train our model, we're supposed to kind of, over time, it'll improve. That's the thing. Oh yeah, and also I made these slides at 2 a.m. and for some reason, ice baby, bias baby seemed funny to me then. In the light of day, I'm not quite so sure it was as funny, but back then it seemed. So if you want a little soundtrack for this discussion, you can play that classic in the background. By the way, just a funny thing, it's totally worth clicking on that video just to look at the wardrobe they were wearing back then. Like early 90s is just the most ridiculous fashion, what they thought was cool. But I think he's literally wearing like a University of Miami like pullover sweater. It's like, why? It's odd. So, but we're going to kind of talk about exactly how that works. Because there's a really cool kind of thing about, like, we talk about like loss functions and gradient descent and convergence, and we even touch on it in project 2, but that's like a whole thing. And I really want to dive into that because it's really cool. And I didn't want to do that. But conceptually, we kind of understand how that works, right? We have our model, we start with a basic thing. As we are training that fit function, we're taking that data and we're sort of fitting it, getting better, trying to deal with the bias. So again, that's probably going to be next week unless we kind of get derailed with some other topics. But that's, for now, that's what I'm planning on doing next week. What I really, no, I want to go to the next slide. I don't want to actually play the video. We'll play it if we have time at the end, maybe. The thing I want to cover today is about the other thing. How do we prevent overfitting? Because again, this kind of goes back to this thing. If you let your model, if your whole model, the whole way your model runs, again, we're going to get into exactly how this works, but generally speaking, you're training, the whole idea is you're trying to minimize your loss function. You are trying to minimize the total loss. And so the problem is, if you kind of don't stop it, there's nothing, it won't know when it's overfitting. It will just keep running until it has minimized the loss. And so, you kind of get this situation here where it just keeps going and going and going and going and going. Okay. So what we kind of need to do to prevent too much variance is we sort of want to put some brakes on our training, on our loss function. We want to try and say, okay, it's good that you're trying to reduce your loss. It's good that you're trying to do that, but we want to make sure like you don't go too far with it. It's kind of like if you think about the analogy of riding a horse, you're sort of pulling back on the reins a little bit. You're like, it's good to gallop, it's good you're doing that, but like, let's slow down just a little bit. And in fact, as a result, when you do regularization, you actually will kind of, if you're looking purely at your training metrics, it will not improve the model. In fact, it's designed to hurt the performance of it when it's being trained. But the result is ideally you kind of end up with something that generalizes, because again, that whole noise to signal ratio, it's capturing the pattern without overfitting. And again, here's sort of a classic example of it, right? This is kind of the ideal thing. We want it to kind of converge on sort of the general trend without going crazy and custom fitting it to the point where it's crazy. So that's generally speaking, this whole idea of at a high level regularization. That's essentially what we're doing. And then there's an example. One of the things I have you play around with your parameters is at some point I have you, for one of the examples, I have you set your penalty to none. And essentially what we're doing is we're turning off the regularization. We're saying, in that case, just run to completion. Just keep going, and just don't stop. Just keep going until you have totally minimized your loss function. Don't even worry about it. Just like do it. Gosh darn it. Okay. So that's sort of, and one of the things I kind of want you to explore as part of that is like, how does that impact? How does playing around with allowing your penalty function to occur, allowing your data to, your training data to converge without imposing a penalty, like how does that impact your performance? And just kind of looking at that. But now let's talk about sort of how we can reduce the complexity. Because if you think about your model as being a, to use the example of an SVM where you're looking at like a quadratic hyperplaning or something. So what are sort of ways in which our models can become complex? And generally speaking, there's two ways to do it. The first way is we can sort of have an overly complex polynomial. We have sort of in our little multinomial term, we have sort of a number of X terms, right? As the number of X terms go up, the overall complexity of our model increases. And so sort of one way in which we can simplify it is just try to kind of reduce the number of features effectively in our data set. That's number one. Number two, we know that the magnitude of the coefficients impact the degree to which any one feature will sort of skew the data. And so maybe we try to constrain, we don't change sort of the number of features, but maybe we try to constrain the magnitude of the coefficients associated with any one feature. So it's the idea, again, that like no one feature can kind of completely radically distort the values that we're getting. And at a very high level, that's exactly what we're doing. And I know that this was covered in lecture. So forgive me if this is a little bit of a repeat, but again, this is covered pretty extensively in homework too. And so I did want to sort of make sure that this is covered effectively for you to be able to solve this. But that's essentially what LASSO and Ridge do. So LASSO is an L1 penalty, and it deals with precisely this idea that you have too much, your term has too high of a dimensionality. And here you sort of impose a penalty for just the absolute sum of your coefficients. And the way this term works here, so here we have, so let me just kind of explain what this is, because I actually just screenshotted this from the homework. So this is a hypothetical question in the homework. So this says we have our loss function here. This is our general loss function. And I believe this is just a mean squared error, where you have your predictive label minus your actual label squared over sort of your total n number. So you have your loss function here, but then you add an error term to it. So remember, if your goal is, so the way these kind of regularizations work, you have your loss function here. Your goal is to minimize your loss function, to produce as little error as possible. But you also add these error terms here. And so here we have our, I think it's a gamma, I think. But anyway, that's your sort of your penalty coefficient. And we'll talk a little bit about that in a moment. times, in this case, and this is your L1, and we'll go into the specifics, and this is your L2, and we'll go into the specifics of that as well. But essentially, it's the idea that theoretically, these are kind of counterindicated with each other, that even as we're pushing this to be its minimum, if we do things that increase the complexity of our result, we're going to push up the penalty. And so overall, it's going to kind of balance itself out, is the thought of kind of how these sort of functions counteract each other. So how does a lasso function work? So again, here we're penalizing the total number of features you have in your data set. And so you're just simply taking a sum of the coefficients, multiplying it by your penalty term, with the idea here that what we really want to then do is try to zero out as many coefficients as possible. We want to try to, and effectively, if you have a zero, if your coefficient value for any one term is a zero, you've effectively removed it from your data frame, right? You haven't literally purged it, but by setting the coefficient to zero, you've essentially zeroed it out. So that's what a lasso term here does. Ridge term focuses again on the magnitude of it. So again, it takes the square of, it sums up the squares, the coefficients of that, and then it returns, and then multiply it again by an error term. And then it sort of returns that. And then, of course, it's worth noting here, I think sort of the differences in terms of function that an absolute value serves versus a square serves. And we talk about this with like RMSE versus MSE, and we're going to look at this with some other things like a log loss and some other things. But generally speaking, what's the advantage of one versus the other in terms of its approach? What do you guys think? Okay, I'm just going to give it to you then. So it's important to note that so lasso does drive the coefficients to zero. That's the important thing. Ridge does not drive the coefficients to zero, but it does drive to minimize the coefficients. That's the goal with what you're doing with this. Lasso tries to remove the number of features in your data set effectively, because again, if a coefficient is zero, you've effectively removed the feature. Ridge doesn't outright remove it, it just reduces the magnitude. So the first thing that's important to note here, and you kind of have to do this no matter what you're doing with your error term, is you need to correct for the magnitude of the error, the directionality of the error. So that's kind of the first thing you need to know. If you think about like your MSE curve, so there was our predictive line right here, and then we had error terms above it and error terms below it. And if you're not correcting for the sign, you could create a scenario in which positive errors are being canceled out by negative errors. And what you're really interested in is the absolute value of the error, not the relative sign of the error. So we have to correct for that. There's just different ways of doing it. And as Manik pointed out, squaring it does a particular thing. By squaring your value, you disproportionately punish high valued coefficients. Right? You kind of see that. A coefficient of the difference between, so if you think about like in this one where you're just taking the absolute value, you treat a 4 and a 3, there's only a slight difference between them in terms of the resulting error. And that's why it does kind of push to eliminate things, but it doesn't sort of disproportionately punish any one of those. Whereas here, you jump from a 9 to a 16 just by that one index term. So clearly it disproportionately impacts high sort of valued coefficients. So that's why, both of these are kind of correcting for it, but the way in which they do sort of dramatically impacts the way in which the underlying performance thing. So here, we're not really treating any one feature above the other. We're just trying to kind of eliminate as many and push as many to zero as possible. Here, we're specifically interested in the higher order ones because they disproportionately affect it. And that's kind of the result of those different approaches. And then again, the last thing I want to talk about here is these penalty functions. So this just defines, right, so simply because I have an L1 or an L2 doesn't necessarily mean they will dramatically impact my overall loss function. The thing that really matters is also the magnitude of the associated penalty. And that's also a parameter that you can oftentimes tweak. So, if I want an L1, but I don't necessarily want it to be overpowering, I can sort of set a very low penalty function. Yeah, and so, and by the way, so then you're asked in the thing, like hypothetically, what if you use both? And that's going to be a homework question. And that is the homework 2 question. Is it like, what happens if you're given both? And, you know, is there a good thing or a bad thing with that? To my knowledge, you only do one or the other usually. You wouldn't do both. And it really kind of just depends then on what you're trying to correct for. So it's more hypothetical in that case. In fact, most learning models like scikit-learn, I think, just only allow you to do one or the other. So yeah, so that is more of a theoretical thing, but that's what we're doing with that. Okay, so that's normalization. Again, you're asked a little bit on the project. You're asked sort of the one conceptual model where you turn off your penalty, but then in the homework, you're also asked about this. But hopefully this gives you kind of a foundational basis that when you're looking at it, you're like, oh, okay, I know what this is asking. I know what it's trying to do. Any questions on that? Man, I feel like we're covered a lot today and we're not even done yet. This is crazy. I don't even, are you guys good doing, well, let me ask you this. So the rest of the course, I have a section on the cross-validation and doing that. But let me kind of just take a quick survey because it is already 1:20. You guys good doing that? Do you want to do KFold? Do you feel like you know it? Would your time be better used elsewhere? Like I can always push this if you want to talk about something else. Okay, since I'm not hearing any overt objections, let's do KFold. Cool. And you know it's going to be a good segment when we get a Mean Girls reference in there. I mean, you just know it's going to work. So when we first started doing our modeling, we did that train test split. And you know, and that's kind of just like our quick and dirty way of doing it. We just take our data. Sometimes we would shuffle the data and then we would just divide it. And we would do a 70-30, 80-20, pour some of it into training the model, and then just do our testing for validation purposes. However, the result of this, as we've kind of frequently discussed, is that it really kind of can create significant issues, both in terms of balance and bias. So balance, if it just happens to be that the way you've carved the data creates sort of a disproportionate ratio of some of your labels, that could be an issue. And then of course there's bias issues if it's just not representative of not only the broader universe of data, but also of your particular sample, you know, particularly among your test data, because typically that's only like 20% of your thing. It's, you know, you're kind of playing with fire to assume that 20% is going to be representative not only of the broader data that you have, but then also the universe of data. So, you know, clearly that's problematic. And I kind of just mentioned this here, but like, I know when we've just good practice for our train test split we've talked about has been doing your random seeds. And remember the whole point of the random seeds was like, if you rerun your model, it should ideally, even though it's randomized, because you've seeded it, it will give you a consistent splitting. And so ideally you will replicate your performance. But you know, one easy thing to do is just turn off random seeds and just rerun it. And you're going to see like your results are going to vary dramatically if you turn it off. I don't know if it's worth me showing that. Why not? So let me, where's my train test play? Okay, so, oh, do I not have, where's my, oh, I think I defined, did I define random seed up here? I don't know. Okay, whatever. I'm not going to waste time on that, but you can test that on your own if you want to, because we're running out of time on this. So let me just ask you kind of really quickly. Do you remember we did cover this one kind of way, one approach that we had to intelligently split our data? Do you guys remember stratified shuffle split? And so that was, I'm just going to give it to you. That was the idea that we know, even though we're doing this randomly, we want to do it exactly. We want to do it in a proportionate manner. So if we know that there are particularly categorical features, if we know that we want those to be represented in how we split, we can do that shift. And so the example we had given was with our Airbnb data. We had, we have our 5 New York boroughs. Manhattan, Brooklyn, Bronx, Queens, Staten Island, right? We have those boroughs, and we want to make sure that both our training and our test data include a proportionate sampling from all of those boroughs. So we don't get a scenario in which all of our Manhattan data ends up in the training thing and all of our Staten Island data ends up in our test data. And that just completely throws it off, because obviously anything that's going to train on Manhattan is going to be completely inaccurate when you're trying to do something like Staten Island. Right. So that was kind of the first thing we did. The other thing, and this is what we're going to learn, is the whole notion of cross-validation. So cross-validation is just the idea that you sort of resample your data and kind of run it multiple times to do that. And so this is kind of a nice visualization here. So we have our data. So we can sort of carve it up this way, training and test. Then we can do training, but this is our test data. And we can do training, test, training, okay, and so on and so forth, right? And this way we've kind of done that as sort of however many, that the K there is just the number of cross-validated times we want to do. And generally the way this works is you can kind of shuffle your data. Once it's shuffled, you would then split your data into K groups, just like this. For each group, you take your training and your testing, you sort of run your model, you train the model independently. This is kind of an important thing, because I didn't, when I first learned about KFold, I got confused about this. You never sort of apply the results of one model to the other model. The idea is that you just like de novo train your data, test your data, get the results, run it again, train your data, test your data, run it again. And then you just kind of aggregate your results across your sort of exercise, and you try to see like consistency, how it performs across its things. So it's again, you're trying to, just like with the single holdout, you're trying to estimate your model's predictive performance against unseen data. But what you're trying to do is you're trying to correct for the inherent biases that might come if you just do it one time. If you just do that single thing, again, all the things we were talking about balance and bias, ideally, you're sort of minimizing that, because you're saying, you know what, I'm not going to leave this up to chance. I'm just going to systematically run this against as many different partitions as possible. And I'm going to just see how its performance kind of happens just across elements. So, and then I mentioned like you can totally do additional extensions to cross-validation. And one of those is stratified KFold cross-validation, right? Which is the whole idea of not only do we want to do a KFold cross-validation, but we want to make sure for each one of these KFolds, we're still stratifying our data. So again, to use our Airbnbs, we want to make sure, just because we're carving this up there, we want to make sure that each carving still proportionally captures New York neighborhoods properly. So let's go back to our data. Let's go back to our little avocado data, and let's look at specifically cross-validation. And again, hopefully this will kind of give you a nice visualization for this. But let's define an array, a nice kind of 12 value array here. So Kedar, let me just show this example first, and then we'll talk about your question specifically. So, and then I'm going to split it. I'm going to do 4 splits, and then I'm going to do kind of the split, and I'm going to just output it. And so you can kind of see, hopefully you can kind of visualize intuitively exactly what I'm doing. So in my first split, I'm carving out my first 3 things are going to be my test, and then the latter 9 are going to be my training. And then I take the subsequent 3 as my test, and the residual as my training, the third sort of quarter as my test, the residual, and then finally I run 0 through 8 as my train, and then the last 3 as my test. And so I think it's intuitively, and you can kind of see the exact same thing here. So I take our own little avocado prepared thing, and I'm printing out. So here what we're printing out, by the way, is we're printing out the index values. So you're just seeing like, so in this case, it starts from index value of 0 and runs up to 4,562. And then our training starts at 4,563 and runs till 18,248. And then again, just like this went 0, 1, 2, 3, 4, 5. Again, here we start at 4,563, run till the next quartile. And then this is kind of the residual, next quartile. And then finally, this is sort of our first 3 quartiles, and this is the last quartile. So hopefully that kind of helps to visualize just how your data is getting carved up. And obviously, because we're not doing any kind of stratification to this, it's just doing this systematically. As you can see, right now, the KFold is just doing it by index value. And that, by the way, is why I do mention it can oftentimes be important to do a shuffling of your data as well. Because as you can see, because the KFold does this by index value, if for whatever reason, and you can see a lot of instances where your index value will matter for your data. It might matter earlier versus later data entries. It may matter, in terms of the quality, in terms of trends. So it may be problematic. Like if you're looking at data that was collected over several years, just to use an example with New York Airbnb prices, right? You would assume, just again, setting aside geopolitical things, recessions, things like that, you would assume inflation is going to happen, and that rental prices 5 years ago are generally going to be lower than rental prices today. So if you're not shuffling for that, if you're not adjusting for that, maybe that's going to be a problem in terms of your modeling, your training testing. So that's why it's always important to shuffle your data if you're just doing a basic KFold. Okay, so how do you actually get a KFold? How do you actually sort of implement a KFold? So again, not that difficult, but there are sort of a few steps to do it. And then let me so I'm running a comparative thing here. So, and this is kind of what you're asked to do for project 2. So in this case, I'm going to compare my logarithmic regression with my SVM regression. And so the first thing is that I'm doing, so I'm importing model selection, and I'm defining a specific instance of KFold. And again, kind of just similar to what you do with other things, you just define your parameters. So in this case, you're going to run a KFold thing. You're defining the number of splits. You're defining your random seed. You're defining whether or not you shuffle your data prior to doing the split. So in this case, my random state is going to be 42. Yes, I'm shuffling. I'm going to do 10 splits. Then I'm going to define my, kind of just like we did before, I'm going to define my specific model instance. So in this case, I'm going to call like a logistic regression. Here I'm going to specify the solver because the liblinear had good performance. So I'm just going to do that. And then I kind of actually get my results. And so here I'm calling the model selection, my cross-validation score. I'm going to kind of talk about precisely what I'm outputting with those things. But for here, I'm inputting my specific model that I want trained. I'm putting in my data, my labels, and my cross-validation strategy, which again, I've defined here. And the reason I'm specifically outputting my cross-validation score is because, remember, I'm going to run this, in this case, because I'm doing 10 splits, I'm going to run this model 10 times, and I'm going to output results for each time. And so essentially what I'm getting with these cross-validation scores is I'm going to try to kind of get the score kind of across those things. And the specific thing here in terms of what you're looking at, what I'm going to get here is I'm looking at the averaged performance. So in this case, I'm just going to get the results. So I'm pulling the results here, and I'm just going to take the mean of those results and return those. Now, there are other results you may want to look at with a KFold. Like one of the things you may want to look at is whether or not you may look at the variance of your data as well. You may want to look at like the distribution of it, right? Something, maybe the overall performance, the average performance is high, but maybe there are some outliers where it performs really well or really poorly. You may want to know that. You may want to know, max and min. You may want to know like the distribution of it. So right here, I'm just like pulling the mean data, and that just says, what is my average performance across all of these things? So in this case, we find that both of these work pretty robustly and pretty equivalently. But again, there may be other information about your cross-validation that you're interested in knowing. So, okay, so questions on that. And let me, and like you guys are thinking, so Ken, I had the question, what if we end up discarding the best model through the KFold cross-val process? So I think, there's always like, you can talk about like your false positive, false negative thing with this approach as well, right? Is this, it's always possible that you happen to do a false positive where you identify the wrong best model because you just happen to do a train test split and it wasn't proportionate. And it's also possible that maybe by doing this, it would have been better had you just done it once. But I think, generally speaking, this is a more robust way just because it's comprehensive, because you're not leaving it up to chance in terms of how you split your data. You're really trying to say, let's just be systematic and test this on as many different configurations of my data as possible. And so I can't say it'll universally work better. There's always that fluke chance that maybe your train test split will just happen to perfectly align with the broader universe of data. And then if you split any other way, your performance will be diminished. That's always possible, but I think, probably that won't be the case. Awesome. Any other kind of questions in terms of like, I guess, conceptually, in terms of how we implement this? Okay. Yeah. So I know it's kind of a lot, but hopefully, particularly with this code, this will kind of give you what you need to get across the finish line in terms of project 2. Let's see. I think that's all I had. Yeah. Okay. So I think that's all I was officially going to cover. Let me just kind of pause there. Oh, by the way, quick aside, nobody's sending me memes. I'm very sad about that. If don't let me do all the work for this. If you guys got some funny material, please send it my way. But I will. You can say, yeah, please. I'm plagiarizing basically every meme on this deck. Send any meme that you come across that's fun. Please share. Okay, so there's a question of, should we judge our models based on cross-validation, heuristically based on? So I think, yeah. So there's a question about like, how do you judge it? And so I believe you can return. I'm not certain, but I think you can. Right, for that one, I just returned accuracy, but I think you can return a like precision recall for your cross-validation as well. I don't think you're limited to accuracy for that. So you shouldn't be limited in terms of what you return. Now, I think I think a broader question, this was asked in Piazza, is like, when do you do cross-validation? Like, do you do it as part of your model selection, or do you select your model and then validate it? And I think part of the sort of oftentimes the trade-off here, and it's not as obvious when you're doing this because we're not really working with big data. But these are even the avocado thing is only 18,000, which sounds like a lot, but I mean in the universe of big data, like where you could be dealing with literally trillions of data instances, billions or even trillions of data instances. We don't really think in terms of computational tractability and whether or not something is robust enough to do that, but like that does become a problem. And that does become something you need to think about when you're sort of designing your approach. So like something like this with data on this size, maybe it's not a bad idea just to kind of bake in cross-validation as just part of your model selection process. And whenever you're running your models, maybe just cross-validate them rather than just do a train test split. Just kind of have that be your default. I think that's very reasonable. Again, where it becomes problematic is when you're getting into, data questions where you have actual significant amounts of data and running that cross-validation may actually become, it'll just become intractable at that point to kind of run that on the scale of the data you're looking at. And I think at that point, you sort of need to, right, there's a whole kind of other strategy around how to kind of build your models around big data approaches. But one of the things you kind of have to think about is maybe being more strategic about taking these steps. Like maybe in that instance, one approach would be, maybe train your model or like train, a concert of models, and then maybe just like cross-validate a few of your top candidates, which is kind of what we do here in this project is we say, okay, well, you've played around with different models, just take the ones that generally have performed well and cross-validate those and just do that as a confirmation step to say, as a sanity check to say, yes, this performance is consistent, right? That's kind of one approach to that. So yeah, and then there's kind of an interesting question about like overfitting. And so I think so the short answer is that so let me just elaborate on it. So if you have, so the guy, so Monica is asking, like, what if you have trillions of instances of data? Like, is it possible to overfit? And the short answer is yes. And it depends on what those trillion instances are. And maybe trillions is too much. I think billions may be a better sort of a thing to do, because yeah, at some point, I guess even that becomes sort of ridiculous. But let me give you an example of this. We would be dealing with oftentimes, like, we're taking readings of a sensor, and maybe the sensor is sampling every few seconds, or even like on a sub-second level. And then we'd be sort of monitoring people for like a period of a few weeks. Well, we may get millions or even billions of sensor readings for that. But that doesn't necessarily mean that in the universe of data, that's actually a representative sampling. Because if you think about it from the perspective, we're still only following one individual for, let's say, a week. So when you put it into perspective, you're like, yeah, I have billions of discrete data points, but that's not actually useful. It's like we did that when we were talking about like metrics. There was that I think there was a Doctor Who joke where it was like is 4 a big number? And it was like, well, it depends. Dollars, no. Murders, yes. And so it's kind of the same thing with the data. Like, it really depends on your denominator there. Like, yeah, billions could be a lot, but it really just depends on the universe of data. That could be an exhaustive thing, or it could just be a really small subsample because the data is just so massive at that point. But, okay. Yeah, so any other questions? Yeah, ask me anything. I mean, you could theoretically ask me anything about anything, but like, if you have anything specifically about projects or homeworks, this is kind of your time. Yeah, whatever you guys want to talk about, this is your discussion.
I have a question about the project.
Mhm.
I found that like sometimes when I reran the cells, like I would have different models perform like much better, and then if I ran it again, it would be like different, and like I wasn't sure if that's okay.
Yeah. Okay. Well, so firstly, that's, I guess, kind of like so let's talk about what's happening there. So I mentioned a random state bit, and you'll see it's like you have this option with your train test split. You have this with these other things, and so the whole idea, if you use, this is what's known as a random seed, and the idea basically is like, even though you're splitting your data randomly, if you sort of seed it, you ensure consistency. It says that even though this is random, once I've split it once, I'm going to continue to split it the exact same way, even if I rerun the data time and time and time again. So because you don't have your random state defined when you do your train test split, every time you do that, it's like shuffling your data in a new way. And so that's why your results are changing. And so in like a weird way, you're basically just doing a little bit of a cross validation, because like the first time you ran train test split, you got this data. And so you got certain performance results. Then you ran the model again, but this time it split it this way. And so your results changed, and so on and so forth. So in like a weird way, like you kind of have sort of showcased exactly why train test split can be so haphazard, and precisely why something like a cross validation is so important. But I guess the specific question about like for the performance of your models, that wouldn't impact your grade specifically, because we're not treating, again, we're not like grading you specifically on like your threshold of performance. We're not saying, oh, you need to achieve a minimum 80% classification ratio in order to get the grade. Like, we're not telling you to do that. And to the contrary, precisely because you have this like random seed issue, and precisely because we're asking you to pipeline your data differently, chances are people will get very different performance results. And that's completely okay. And it's not going to be wrong if, for instance, I'm getting a logistic classifier accuracy of 83%, and then you run it and you get a accuracy of 72%. That doesn't mean that you've necessarily done something wrong. It just means that the particular choices you've made in terms of pipelining your data, or how your data has been split will impact the result.
Okay, that makes sense. Thank you.
Yeah, absolutely. Okay. Oh, wait a second. Okay, so, so I'm getting a question about deadlines. So just send me an email about that. And then I see there's a question about like health related projects. Can you health related project? Yeah. Can you send me an email about that as well? Because I definitely would be interested in hearing more about that. But so let's see. And then is there any other questions or just things you want to talk about? Okay, if I'd like to ask about just right now, that'll compute. Okay, so look like is a logarithmic curve. Okay, yeah. So I do have there's like a lot to unpack there, and actually I will say I do have a bunch of slides prepped for logistic regression. If that's so, actually, so let me ask the I guess the rest of the cohort who's here. Is logistic regression something you guys would be interested in covering more extensively, maybe in a future week?
I think it'd be pretty helpful.
Okay, cool. So, oh, that's awesome. Okay, because I actually have a bunch of slides about that. So that's awesome. I'm gonna. And so then that makes next week. So I guess maybe next week we'll let's cover logistic regression as well, and then let's also talk about like loss functions and gradient descent and convergence and things like that. I think maybe that might be a nice topic for next week, because like there's a lot. So in your question, there's obviously like a lot to unpack there, and there's like a quick answer. There's the 30-second answer on logistic regression, and then there's the longer answer. And I think you're kind of want to get a little bit into the weeds of that. But yeah, so I mean, like there's a lot to unpack there. So okay, so Monica, do we have permission to defer that slightly till next week? That discussion? Okay, cool. Yeah, man, there's a lot to unpack there, but like I'm glad you're thinking along those lines because like yeah, it's like it's really cool and it's I think it's kind of deceptively one of the downsides about something like scikit-learn is like it makes these learning models look so similar just because from a coding perspective they're functionally equivalent, right? Like you use the exact same like coding parameters to code a logistic regression as you do an SVM, and the exact like and then a KNN and an AEP. It's like it's the exact same from a coding perspective, and I think as a result you kind of tend to look at them interchangeably as like, oh, let me just throw a dozen different classifiers against the wall and see what sticks. But like these are very, very different approaches to the problem of classifying data, and they take really, really kind of unique things to do it. So do array and set my pipeline knows right. Okay. Yeah. So Drew, if it's already in an array, then don't worry. I'm actually not. So there's sometimes some issues where like somehow something that you do in the pipeline will kind of break, right? It should by default output a NumPy array. That's what it should be doing if it works well. But like sometimes, and I'm not even sure exactly what causes it, but you can do something that will inadvertently kind of like kill the array, and then you kind of need to cast it to an array. But the good news is if it's already by default an array, then you've done it great. So that's just there, like that's just a catch-all if inadvertently your pipeline has kind of broken your array. That's just kind of a way of fixing it. But if it already is there, then you may return that error that says, hey, why are you doing this? You've already fixed it. Yeah, so Bell, if yeah, if you want to stay on, we can talk about. So I don't mind talking about implementing stuff in the group. But let me just see if there are any general questions, and then if not, so just for everyone's awareness, Belle had some specific questions about implementing specific things in Project 2, so we'll go through that for anyone who wants to kind of stick on for that. But before we do that, let me see if anyone else has just any kind of conceptual questions. Oh yeah, by the way, I hope everyone has a great weekend. I hope you take some time, have some fun, don't work too hard. Like obviously get this done, but Okay, so if there's nothing else, then Belle, the floor is yours.
Okay, thank you. I was talking to the.
Actually, hang on, let me stop
Oh.
recording.
Okay, no worries.